So, welcome, dear participants, for today's session. We can start the session in 5 more minutes. So, I welcome you all. Thank you very much for your kind cooperation. So, let's start the session in 5 minutes. Surya Prabha ma'am, can we start the session?
We start exactly at 10 p.m.
Okay, ma'am. Okay, we'll wait for 2 more minutes.
Okay.
Okay.
Good morning, Dr. Neer Chandra, sir. Thank you for your presence, sir.
Ma'am, can we start? Can I start sharing the screen? My screen for the PowerPoint?
1 second, sir. Just we'll have a formal welcome address and introduction.
Okay.
Chief introduction. Just.
Okay. Thank you.
Just 2 minutes. Yeah, Sharmila ma'am, you can start.
No problem.
Sharmila ma'am?
Yeah, sure.
Yeah, you can start.
Sure, ma'am.
Dear participants, I welcome you all for the forenoon session of day 2 of 1 week international FTP on trends and innovation in Industry 4.0. I invite Mrs. J. Sharmila Devi, Assistant Professor, Department of ICE, AVC College of Engineering, to introduce the eminent speaker of this session.
Thank you, Vinodini. It's a great pleasure to welcome such a noble personality as our eminent speaker for today's morning session, Engineer Narayanan Suresh. So, on behalf of one and all present here, I welcome you, Mr. Narayanan sir. He is a very good personality and is widely known to put in a lot of effort and hard work. Narayanan Suresh was graduated as Electronics and Instrumentation Engineer from Shastra University, then acquired a diploma in business management. He possesses over 18 years of experience in process automation domain. He has been associated with Dell Computers and LAN Instruments, where he began his career. He has been with Egogova since 2008 in various positions. Currently, he is a senior consultant, Flow Solutions, and responsible for business development, consulting and advocating value realization for end users in Middle East and Africa region. He is also an active member of International Flow Specialist Group. He has spent majority of his career time in deploying advanced measurement and automation technology in oil and gas, petrochemical, refining, power and mining, and metal, pulp and paper industries. He has always been fascinated of how innovation and technology simplify the complex mundane problems that human and businesses need to deal with, whilst allowing to focus on what truly matters. He believes and strives to bring the most reliable, latest, and sustainable field through digital technology to the process automation industry. I cordially invite Engineer Narayanan Suresh to share his thoughts on the topic chemical injection and digital oil field IR 4.0. Welcome you, Narayanan.
Thank you, Sharmila Madam, for the wonderful introduction. I hope I can live up to the expectation set during the next 2 hours. Okay.
Sure.
So, can I share my screen and start the slides? Is it okay now?
Yes, sure, Narayanan.
Okay, thank you. I hope I am audible very clearly to the other side.
Yes, clear.
Yes, sir.
Maybe you can mute your mic. Edwin, Mr. Thank you. Yeah. Can you see my screen?
Yeah, visible.
Okay,
Visible.
great. Okay. So, thank you everyone from AVC College of Engineering for inviting me to give an overview on the latest technologies and trends in process industry. Yeah. So myself, Narayan Suresh, been working with Yokogawa for the past 14 years or so. So today's discussion would be focusing on chemical injection and digital oil field. Okay, it's a very big topic. It's a very vast topic. So I will try to give as much as I can, in this 2 hours of session. Yeah. So I'm sure, everybody would be familiar with IR 4.0. Needless to say, you're experts and you are with universities. But my main agenda for today's meeting would be focusing on getting the practical experiences, how IR 4.0 is being implemented. I would say it's in a very nascent stage of implementation. It is not deployed completely, but we are starting to move towards this direction. And I can show you some example. We can discuss some examples of how we are doing it today. Yeah. So the agenda is very small. Yeah. Evolution of industrial revolution with certain examples. And I would like to take one particular subject for today's discussion, that is chemical injection, because I feel it is very important for the people in the university to know chemical injection, because I believe you are from the School of Electrical, but in the field, you have the chemical engineers, mechanical engineers, instrument engineers, everybody working together. So this would give a good overview how different engineering disciplines come together to work, and what are the challenges, the oil field operators face today, and how we can, solve this. And I would like to also introduce to one of the product which I think is unique, and it's a game changer in instrumentation in industry today. And I would like to give you some brief overview of this product, because it's a combination of many functions in a single device. Okay, this is still not mentioned in our measurements technology book like AK Shawnee or all those, because it's a very new technology. So this would be really beneficial for you to know this technology and certain practical cases. Yeah. So please do feel free to ask. If you have any questions, please feel free to stop me and ask. Don't wait till the last. So I wanted to be like more of a discussion than a kind of a presentation, and then you ask some questions in the last. So let's make it kind of interesting. Yeah. So with that, I would like to get into what's the matter in hand today. So we start with the basics. I want to show the evolution of industrial revolution, which we call it as IR. Okay. So I'm sure you would have, everybody knows this, but just to set the tempo of today's discussion, everybody knows before the industrial revolution, there was pre-industrial revolution that was mostly mechanical, and animals pulling the carts, and humans doing mechanical stuff. So with the advent of steam and boilers and other things, that was the mark of industrial revolution 1.0. Yeah. So steam was used to automate most of the tasks, and then with the advent of electricity, We started, electrical machines and mass productions, which would not be achieved only using steam. And that was in 1870s. And everybody knows about that. And the most important, and I would say still we are dwelling in today's world, even in 2023, we are still in IR 3.0 because because the computers came in and the processing power increased, and we could have more processing power in a smaller chip. And we had the computers, DCS, PLCs, SCADAs, and so many things. And that were used to automate a certain routine, which was either in IR 2.0 was done by relay logics and stuff like that. So with the advent of computers, we were able to make things faster and make a closed loop automation. And now we are moving to the IR 4.0. And what exactly is IR 4.0 is, what we will see today. So, in one word, what I would say the difference between IR 3.0 and IR 4.0 is IR 3.0 focuses on reactive maintenance. Okay, so let's say you have many communication protocols from the devices like pressure transmitter, flow meter, many other sensors, temperature transmitters, level transmitters, which collect the process data and give it to your distributed control system. So there are many communications which are used in IR 3.0. That is 4220 milliamp, HART, foundation field bus, Modbus, Profibus, etc. And if you see, most of these communication protocols, they are especially the Modbus, foundation field bus, and Profibus. They are digital. We call it as the field bus. Okay, they are literally high-speed communication, and they can carry many data, from the sensors to the control system. But are we taking the full advantage of the communication speed and the advantages of the field bus technology? No, today we are not. Okay, so that's going to be our discussion. So if you see, we are using advanced protocols like field bus protocols, but still we are depending on reactive maintenance. So the sensor gives a signal to your DCS that there is a fault or a sensor failure, and this means an operator or a technician needs to go from his office to replace the sensor or remove or repair the sensor. So when the sensor is failing, you have a certain downtime in the process. You're not going to have production, or you're not going to achieve a certain desired reaction. So with that being said, this is where artificial intelligence comes into picture, so which we are lacking in IR 3.0. Now, if you see IR 4.0, what is the main thing is, it is digitalization. Why we digitalize it? Of course, the computers understand digital language. We need to digitalize, and data collection. So now in IR 4.0, what we're going to do is, we're going to read the same process information from the sensor, let's say the sensor which we discussed, and we're going to collect the data. Okay, the data is stored in a data dump, and then we have an artificial intelligence which is going to characterize this data and analyze this data, and then it's going to kind of going to say is this data healthy, the census data healthy, or it is deteriorating in signal quality and the functional qualities. It's going to analyze. And now we can set the certain threshold, the performance threshold for this. And then if it's going to reach to the threshold, we are going to intimate the user in advance based on the characterization that this sensor is going to fail. So the operator can be intimated well in advance that something is wrong with my sensor, and I want to arrange a spare sensor, and I'm going to replace it before the process is shut down, so they will not incur any losses because of the process shutdown. Okay, so all this is done by the computers. So why this was not possible in the IR 3.0 was because we had a limited data processing capacity by the processors, and we had many limitations. And since, like I said earlier, the computers are becoming more and more cheap and more powerful and affordable, so it can handle enormous amount of data, and so all this is possible. Yeah, so predictive prognosis and preventive measures. Okay, this is just the theory part of it. So I will give you an example, how this is being implemented in a simple thing. And today, if you go to any refinery, any oil field, or any process industry, one of the main component is the pumps. Okay, and the maintenance guys are always worried about the healthiness of the pump, because if your pump stops, your entire the flow line is going to stop. If a particular flow is stopped, then your subsequent process is not going to work. So that's how important it is to maintain the health of the pump. Yeah, you can see the pumps over here. Now, the pump is a moving part, and it works 365 days, 24/7. And how do we know the performance of the pump, whether it's in an optimum performance or it's going to fail in maybe 1 month time or 2 months time? And should we keep spares, if this pump fails? How do we know this? Okay, so that's the reason. We have some product, what is called as the sushi sensors, the small green thing you see over here. You can, it has a magnet at its base, and you can stick it on the pump. Okay, and this, you just like, how do you put some magnet on your cupboards and fridges, at your home? It's like that. You just stick that magnet, the sushi sensor, on the casing of the pump. That's all you need to do. And now this sushi sensor, it is an IoT based sensor. It collects the acceleration. Acceleration is nothing but the vibration, in layman terms, we can say, of the pump, and then it collects the surface temperature of the pump. The surface temperature of the pump is very important, because if there is any misalignment in the shaft or the bearing of the pump, then due to friction, the casing temperature will increase. Okay, by monitoring the acceleration and the casing temperature, we can find the or predict the healthiness of the pump. Okay, so now these sushi sensors, talk through a protocol called LoRaWAN. Okay, to the gateway over here wirelessly. So you need not put any wire between the sensor and the gateway. And then this gateway is connected to your computer or any other cloud device or a in-premises computer, anything. This is, of course, a wired communication. And then it is collecting the data, and then you can remotely see the data as well. And then we have this piece, which is in the cloud, is a purely software. There's nothing hardware in it. Okay, and then you have the functions for the models. You implement the model. The model is nothing but you give the thresholds and all the other things, and then here is the machine learning module. So this is what we call it as the big data. We collect data over a period of time and then analyze the data and give outputs based on the machine learning and the yeah. So here I'll show you some practical examples what the machine learning does inside and how it gives us a result. So if you can see here, this is the velocity of the pump A and velocity of the pump B. It's another pump, two different pumps. Okay, let's take one thing. And then you have the acceleration of the pump. This is nothing but the vibration. And this is the surface temperature of the pump. Okay, this is a very healthy surface temperature because you can see it's more or less constant. Okay, so, but if you see, the pump B, you have too much of velocity and too much of, accelerations, vibrations up and down. Okay. So now all these things put together on a single chart, and you can see the vibration is increasing over a period of time, and so is the velocity is increasing. Okay, and if it is going to reach certain threshold over here, then we are going to say failure is imminent. Okay, so that's what the machine learning is, a smart piece of software behind which is running and analyzing the data dynamically and giving you the status that the pump is, whether it's in the normal zone or in the abnormal zone. Once the pumps comes into the abnormal zone, the operator can be notified well in advance to take a proper shutdown procedure, and he can intimate the production that the pump is going to fail. Please allocate your production accordingly. We are going to replace the pump and we are going to have 2 hours of outage time. Give us 2 hours. So they can plan well in advance. So now what happens if it suddenly fails? If you don't have this technology, then it will take 10 hours. He might not have some pump in the spare, and the production will stop for more number of hours, and it is eventually lost to the company in terms of financial things. Yeah, so these things help the operators and the maintenance to have a peace of mind and plan things ahead and see clearly ahead. So which this was exactly not available in the IR 3.0, is where you will just know after the pump fails, you will get a diagnostic pump has failed. So that is not helping us. So with IR 4.0, I think so in one small, a benefit of it is like a case study, which I'm trying to say over here is you can see things clearly in advance. Okay. So any questions so far, please, feel free to ask. Yeah. So.
So you continue, sir. Participants will ask the doubts at the end of the session.
Okay. Thank you. Thank you. Okay. So more example is molten sulfur transfer line. Molten sulfur transfer line. If you see a refinery, the basic functionality of a refinery is to refine the crude into naphtha, petrol, kerosene, diesel, heavy residue, by the fractional distillation unit. Okay. But most of the time what happens is, in any refinery, you will have a process called the cross process. Okay. Maybe from the chemical engineering department, people would be knowing this. It's a very important process, and that is the the sulfur recovery. So what happens is the crude which is coming from the from the ground, from the oil wells, the crude are termed as sweet crude and sour crude. Okay, sour crude is nothing but it is having more H2S content in it or sulfur content in it. Okay, so typically if you see in Saudi Arabia, we have the Arabian light crude with a density of 760 kilograms per meter cube. But if you go to Kuwait and some parts of the region, you have more amount of sulfur in the crude. So sulfur should be removed from the crude before the distillation, or during the process of distillation, it should be removed. And so definitely you have a process what is called as the H2S should be removed and all these things. So Claus process is there, so to remove the sulfur contents from the oil. And the removed sulfur, it's in a very hot state. It is in a molten sulfur, and that needs to be transported to some other place, or it is used by the fertilizers industry, for preparing their end product. So when molten sulfur is transported, the keeping up the temperature in the transport line or the pipeline is very important. So the entire pipeline is heat traced. Now, if there is any insulation failure in the line, then the heat will drop, the temperature will drop, and then the entire line will get stuck up, because once the temperature drops for a molten sulfur, then it starts solidifying. So monitoring the temperature along the complete pipeline requires very accurate sensor. And so again, we can use such sushi sensors to monitor the entire temperature of the pipeline and all these things. Yeah, it's a very important process in a refinery. And then one thing is like another example is oil well downhole sensing. In oil well downhole sensing, this is nothing but below the oil well, you have the external casing, the tubing, and the annulus, and which extends to several hundreds of meters below the surface of the earth. And now monitoring the temperature and monitoring the corrosion of the casing material is very, very important, because when the temperature increases, the rate of corrosion increases, and there are so many other parameters over there, so which needs to be maintained. So today it's very difficult to do that, and to read the corrosion levels of the casings and the tubings, and also the temperature profile across the tubings and the casings is very important to determine the rate of corrosion. So the integrity of the oil well is protected, and people know in advance if any failure is going to happen. So that's also a very important example of predictive diagnostics, where you need to know things in advance. Okay, so these are some of the examples. Okay, so that's an introduction to what is IR 4.0 and the differences between IR 3.0 and IR 4.0. And of course, in IR 4.0, we are using many robotics. Why we are using robotics is certain places in certain process industries are hazardous and hazardous in terms of not only in terms of explosive gases, in terms of the sound in decibels because of rotating machineries and compressors and so many things which are running. You literally need to put earplugs, and due to the heat generated by the machineries, it's very difficult for humans to access those areas. So there are field robots which can go to the site and which they have a camera on them, and they can do the surveillance and basic monitoring. And it now the image recognition and image processing is a very big hot topic. So it captures an image of the process, and then it compares it with a standard or a correct image, and then it does an image processing, and it says if it is within certain tolerance, it says it's okay. If it's not, it sends an alarm. So the routine inspection and other things can be done by a robot, and this routine can be automated. For example, if you have a flange, two pipes are joining with a flange, and maybe the integrity of the nuts and the bolts in the flange, is it okay or not? It can be done by robots instead of a human, and this can be tied up to the maintenance scheduling system, or the such things in the process. Okay, so that's an other thing which is happening, yeah, in IR 4.0. Okay, so coming back to our main topic, what is chemical injection in digital oil field? Okay, so the main objective of having a digital oil field, it's a very big concept, but in a nutshell, basically what it is today's global political scenarios and the relationship between different countries, oil price and determining the oil price is very important. Okay, so how the oil price is determined in the global market is, when you say today a barrel of Brent crude is, I don't know what's the live rate today, but let's say $100 a barrel of Brent crude. So how this is determined is determined basically on the production of the oils in countries like Saudi, Kuwait, UAE, and certain other countries. Okay, because these are the biggest producers of oil. So if the oil price needs to be increased, they simply need to kind of reduce the production of oil. So for me to say, okay, today reduce the production of crude in certain country by 100,000 barrels, with a push of a button, you can do it. So this is the ultimate, objective of a digital oil field, to control your production and, to closely align your financial objectives with the technical data, okay, in the field, like what we engineers do. Okay, so this means every aspect of the oil field needs to be automated. Okay, automated is one thing. Okay, it's a glossary of IR 3.0. So now it is called as an autonomy. So we call it as industrial automation to industrial autonomy. Okay, so that's the term which is being used. So one particular thing where I want to kind of focus on today is chemical injection, and you can see how this can be clearly a part of digital oil field. Yeah. So now some chemicals are injected into wellhead, okay, to achieve a certain action. Yeah. So chemical injections are used. Okay. Now before I go over there, you have a chemical, and you have a pump, and this pump pushes the chemical into the process. Okay, so now if you can see over here, chemical injection is used in all the industries, upstream oil and gas, refineries, petrochemicals, minings and metals, water and water desalination and treatment, and power plant. Okay, all the industries use it, but our focus today will be on oil and gas production applications. As you can see, you have the wellhead. I've just shown two wellheads over here. Literally, there are 500 or 600 wells which are producing the oil, and then it comes to a common manifold. Then it goes to a production separator. This is a three-phase separator. I can show you some examples of what happens in a separator. And here the oil, water, and gas are separated, and then the gas goes to the gas treatment, and the water goes to the water treatment, and the oil goes to the oil treatment facilities. Okay, so this is still not a refining; it is just a treatment. We can discuss this later. Okay, so this is what we do in a typical oil field. Okay, producing and separating the oil and treating the oil. Yeah. So what happens is when we are just give me a second, please. I'll just just have some water. Yeah. Sorry about that. Yeah. So you have hydrogen sulfide, chlorides, carbon dioxide, and oxygen, which comes from the from the produced oil. So I was mentioning to you earlier in the downhole below the wellhead. That's below this wellhead over here. Maybe I'll just take some pointers there. Yeah, below the wellheads, you have the tubings and the casings, and all these things might get rusted or corroded because of this presence. Okay, once if your tubes are going to get corroded, and then that's the end of it. So your well is going to shut down, and it's going to you're not going to produce anything, and then it's a production loss. And then to change the entire well casing tubing, it's going to take months. Okay, and for months you're not going to have production. So that's why these are some undesired effects over here. Okay, just want to show. Just a second. Oh, sorry. Yeah. So how, and then it's not only the corrosion, and then you have something called the hydrate formation. Hydrate formation is nothing but you can see an ice-like thing. These guys are pulling it out from the pipeline. So this is like solid ice. Okay. So this forms in certain gas-producing wells or associated wells. So such hydrates can block the oil flow, and then you'll have production loss. And then you have a wax formation, because certain oils have a tendency to have wax. Okay, and that can also plug your pipelines and stop production. And asphaltene. Okay, asphaltene is very commonly found when produced in heavy crudes and other things. So this can form like a scale, inside, and block the flow of the oil and other things if not treated. So scaling and all these things, you need not wait until the entire pipe is blocked like this. Even if it is forming on the circumference of the pipe, it is going to reduce the inner diameter of the pipe. And when it is reducing the inner diameter of the pipe, it is going to create a pressure loss. And if there is a pressure loss, it is not very good, because the pumps have to work more, and your production velocity also the production, sorry, not velocity, the rate of production is also going to deplete, come down. So that's not very good, and eventually you're going to end up spending more energy. So these are detrimental to the production of oil. And then you have the process of separation over here in the production separator. So in production separator, when the oil comes into the separator, you can see over here, lots of foam will be present in the oil. So if the foam is present, the oil and water will not separate efficiently. Okay, so you put a chemical to, break up this foam and escape this foam. And also you put a chemical for increasing the water and the oil separation rate. Okay, so now why I'm telling you the foam is very important, is detrimental, is because in a production separator, if you see, you have the water, oil, and gas leg. Okay, so now the gas goes through the gas treatment after the separation. Now what happens is, if there is a foam, the liquid carryover will happen. So liquid also will go inside the the gas treatment, and if you have certain amount of moisture content over here, then it can be detrimental to the process, because compressors cannot handle over a certain percentage of moisture. Even though they have filters or anything, you have to frequently change the filters. So that's the reason, to avoid liquid carryover in gas leg, you need to break the foam and have a proper separation. Okay, to achieve all these things, chemicals are injected. Okay, scale inhibitor, corrosion inhibitor, hydrate inhibitor, chemicals are directly injected into the wellhead. Okay, so they will try to inhibit the corrosion or scale formation or hydrate formation. And demulsifier is a chemical introduced at the inlet of the production separator, because it breaks the it reduces the surface tension between the oil and the water, and separates the oil and the water more quickly. So if you don't put demulsifier, it will take 1 hour for the oil and water to separate. So that means you are going to have a slow rate of production, and it is a kind of, I can say it is a lesser financial revenue. Okay, so we need to keep up a certain rate of production of oil. So we inject a chemical for demulsifier, so the oil and the water separates quickly. And the flocculant is chemical. Oil are going in, oils are in droplets. So you flocculate the oil, you collect all the oil droplets together to make a big a bigger drop of oil, so the separation is more optimum. And antifoam, you first need to get rid of the foam over there, so you put a chemical called antifoam to break the foam and get rid of the foam. And then a biocide is very important. Generally, biocide is sodium hypochlorite chemical, where it is used to prevent bacterial growth or microorganism growth in the oil, because the oil is going to be retained or stored in some place for a particular period of time. So the bacterial growth should not happen. So you put a biocide to keep the quality of the oil. Okay. Then you have oxygen scavengers and de-oilers. Okay, the water which is separated, this water is again injected into the wellhead or injection wellhead. Okay, why the water is re-injected? The reason is, in the oil field there are oil formation, or pockets of oil formation, or oil reservoir. Okay, now how does the oil come up? When there is sufficient pressure under the earth in the oil reservoir, only then the oil comes up. Now if you keep taking the oil out, the reservoir pressure is completely depleting. Okay, how do we manage the reservoir pressure? So we re-inject the water which is taken, and before we re-inject the water into the ground, we have to make sure it is having certain qualities. Okay, um, so that's why we put oxygen scavengers, de-oilers, and corrosion inhibitors, and inject the water down to keep the reservoir pressure. Okay, so that is very important. Okay, so that's why the water needs to be treated before it is going to the reservoir. Okay, so there are different techniques to keep the pressure. There are that we will cover it later, maybe during another session. There are some wells with gas injection, and some well where they inject the oil, the produced gas. Produced gas is nothing but methane. C1, methane, ethane, propane, butane. A part of the produced gas is injected into the well to keep the reservoir pressure and push the oil up. So these are gas injection wells. Or even carbon dioxide is also injected into the wells. That's a separate topic. We'll discuss that later. Okay, so the main objective of this slide is to make sure to tell you that different chemicals are injected in the oil field in different stages to inhibit a certain negative reactions. Okay, like we discussed earlier. Okay, so what happens is, the problem is you should not inject the chemical too much. Okay, overdosing, because overdosing the chemical is going to cost more and disruptions and all these things. Okay. Underdosing is definitely not recommended, because if you are not dosing the chemical in the certain prescribed rate, then we are going to have the scaling, corrosion, plugging, production stoppage, or tremendous shutdown and maintenance cost. Okay, so you can see underdosing might cause corrosion, hydrate formation, and all these problems. Yeah, fouling of the equipments during solid deposition. The bigger problem is not only this one. If any scales or anything are coming out, if it is going to the pump, then it will destroy the pump, and then it is a more load on the pump. We discussed the predictive maintenance of the pump, right? This is here. If you can see over here, if the viscosity of the liquid increases, it puts a very high load on the pump. The pump will slip. Okay, and that's not very good, and your pump is going to fail more quicker than its expected lifetime. Yeah, so that's the thing. Yeah, so so I already explained liquid carryover in gas phase due to foam, and all these things. Yeah. Okay, I'll tell you a certain thing. Overdosing is not only associated with chemical cost or overconsumption of chemical, but if you overdose demulsifier, then what happens is again it will form emulsion. Okay, see, this is optimum dosing of demulsifier. If you underdose, then separation is. If you overdose, again you are going to form emulsion. So you should do the correct dosing. Okay, in some refineries, to inhibit hydrate, methanol is injected. In some refineries, if more than 40 ppm methanol is there, they will not accept the crude from the oil field. Okay, so overdosing of methanol, that is hydrate inhibitor, is also not accepted, because it compromises the quality of the crude which we are sending to certain refineries. Okay, so this also needs to be bear in mind, that always overdosing is not good. Okay, so just to give you an example, over here, a well produces like 3 million standard cubic feet per day of natural gas. Okay. Now, to stop the hydrate formation, we must inject a chemical called methanol at 130 kilogram per million scarf. Okay, million standard cubic feet. Okay, so if you calculate it for 3 mms CFD in terms of volumetric flow, it is nothing but 16.25 liters an hour. Okay, 130 kilograms of methanol. So now 1 liter of methanol is costing 25 cents, quarter of a dollar. Now, it's impossible for an operator to set a injection rate of 16.25 liters an hour. So the operator blindly rounds up at 20 liters per hour because he wants to overdose, because underdosing will cause production stoppage because of the obvious reasons I said. Now, just by injecting 3.75 liters an hour, okay, excess, it is costing him $8,000 per year per well. So on a small oil field, at least you will have 200 wells. So that is $164,000 a year. This is only the cost of over injection. There are several other costs which I will say. So this is what we want to stop, because over injecting just like this is not doing good to anybody. Yeah. Okay, so this is the background of chemical injections and why it is very important in an oil field, because a slightest miscalculation will stop the production altogether. So now you would be able to appreciate the importance of the chemical injection in an oil production field. Okay, so today, how maybe IR 3.0, let us say, how chemical injection systems are implemented, that is aligned with IR 3.0. Okay, I hope so far it is clear and not boring. Please let me know if it is boring, then I can change the topic or
No, sir, it's very interesting.
Okay.
Continue, sir. Okay, sir.
Okay, fine. Thank you, madam. Yeah. Okay, so legacy system, how it is done is, you have a chemical. So these chemicals are made by certain manufacturers like Nalco, G, Suez, Clariant. There are many specialists or experts who manufacture this chemical and supply to the oil field. Now these chemicals are not very cheap. These chemicals are very expensive. Now what happens is, they are using a pump called a positive displacement pump or a controlled volume pump. Maybe if you're not aware of there are different types of pumps, but the main pump is what we know as is a centrifugal pump. Everybody knows, even we use it at our home, that to pump the water from the well to the overhead tank, centrifugal pumps, which we otherwise call as the submersible pumps and so and so. But these pumps are a different kind of pumps, which are called as the positive displacement pump or reciprocating pump. Now, how these pump works is, it takes pockets of, liquid for every stroke. Okay. One, it is like a piston, moving left, right or up, down. Okay. For every stroke of the piston, let's say it takes, say, 1 ml of liquid. So if it makes 100 strokes, how much ml it will take? 100 ml. So like this, for every stroke, the volume is metered in this pump. Okay, clear? So if you are adjusting the stroke rate of the pump, you can adjust the volume pushed by the pump. Okay, so if you keep 10 strokes per minute, it will give 10 ml per hour, or let us say even 10 liters per hour if it is a bigger pump. If you keep 100 strokes per minute, then it will give 100 liters per minute. So this is how the pump works. And there is a certain API. API, I'm sure everybody should know. This is the standards by American Petroleum Institute. They have different standards for different things, and probably we should have another lecture on different API standards. And what different API standards says, if it is for mechanical, it is for measurement. It's a vast subject. So for every instrumentation and process metering and everything, there is a API standards. Okay. So for this pump, API has specified how this pump should be constructed and what are the design guidelines and what should be its functionality. So that is defined, and the pump manufacturers manufacture the pump as per this API 675, and it says the accuracy of this discharge should be 1%. Okay, this is what the API 675 control volume displacement pump says. Okay, so this is a very special pump. Okay, now after the pump we have something called, okay, this is not required, I'm just telling you, we have a pressure relief valve. I'm just going into details. So pressure relief valve, if there is any overpressure, this relieves the pressure back to the tank. Then you have the pressure gauge and you have a pulsation dampener. Why do we have a pulsation dampener over here is because this pump works in stroke, on, off, on, off, on, off. So on, off, it is like a pulse signal, okay, in electronics, okay. So during an off, you'll not have flow. So now this pulsation dampener tries to, it acts like a capacitor over here, and then, it tries to, have a smooth flow even and not have this, pulse signals over here. You'll have a steady state flow over here. It acts like an accumulator over there, to have a steady state flow. If you don't have the pulsation dampener, you will see this pressure gauge. During an power stroke, it will show 20 bar, and during the non-power stroke, it will show 0, 0, 20, 0, 20, 0, 20. It will be fluctuating. But you have a pulsation dampener over here, it will steady state show 20 bar. This fluctuation will not be there. Okay, that's the reason. So here you see there is no flow meter, no control valve, nothing over here. So the pump is doing two functions over here. It is maintaining the desired pressure, and it is also trying to control the flow rate over here. For example, if you say 20 liters per hour, it will try to discharge 20 liters over here depending upon the stroke length you set. So now let's say this this well is at 100 bar. Sorry, my handwriting is bad, especially on mouse. Okay, this well is at 100 bar pressure, and now if you want to have, let's say, 10 liters per hour injection rate, this pump should be at least at 110 bar. Okay, operating here. So the delta P should be at least 10 bar. Of course, it is Bernoulli's principle. The higher the delta P, the higher is the flow rate. So that's how it operates. Yeah. Okay. So now in this type, the injection rates, operator needs to go to the field and adjust the stroke on the pump. Okay. Now you have some pumps equipped with variable frequency drive or stroke controller. So you can send from the plant DCS the VFD to control the VFD, and so the VFD in turn controls the stroke length, and this will be like 4 to 20 milliamps analog signal communication, and where you can adjust the pump stroke length. Yeah. So this is a remote control. Okay. So you also have cases where a single chemical is injected to 3 injection points or 3 wells. And you can see over here, one motor is sufficient, but you need 3 pump heads. Okay, one motor is sufficient, but you need 3 pump heads. Okay, and then you can have a Coriolis mass flow meters over here. And the Coriolis mass flow meters work on, the Coriolis technology. Again, we can keep it as a separate subject. It would consume one day if we discuss about Coriolis mass flow meters and its working principle. So here the pump discharges the flow, and the operator can see what is the injection rate that is going on currently to the particular well. Okay. Okay, what are the challenges that are faced with the current chemical injection system? Okay, this challenge is something when we have spoken to many oil operators and maintenance guys, they all say that the injection rate drifts. Okay, and there is overwhelming manual operation and pump issues and leaks. Okay, so see, when they say overwhelming manual operation means a person from here in the control room, maybe typically the control room will be like say 2 kilometers away from the field. So he has to travel from here to here in a desert and then adjust the stroke length of the pump and then go back. Okay. Now once he adjusts the stroke length of the pump, let's say he put at 10 liters per hour. So maybe after 2 days, it will start becoming 9 liters per hour, 8.5 liters per hour. It starts drifting down. Again, this gentleman has to come from here to adjust the stroke length of the pump and go. So this is overwhelming manual operation. I'll tell you the reason why the pump is drifting. Okay, why the pump drifts. Okay, even if it is a remote operation, it is still stupid. That every time he needs to keep in track that whether the pump is drifting or not. See, if you see the essence of it, everything is a reactive thing over here. It's not a proactive, like IR 4.0. Okay, everything is reactive. That's the main point I'm trying to drive over here. So, uncertainty in chemical injection rates, overwhelming manual operation. This is what they are mostly frustrated with it. Pump issues and leaks, maintaining huge inventories and spares of pumps of different sizes. Okay. So, what I mean by injection rate is, let's say the set point is, let's say 10 liters per hour. Okay. Liters per hour. If you put a set point of 10 liters per hour, it is expected that the pump should hold at 10 liters per hour, plus or minus 0.2 is okay. But the pump drifts like this. Somebody has to go and correct it. Once it's drifting, somebody needs to again set it over here. Again, it will drift. So this is why this happens. Okay. So generally in the posture displacement pump, there are 2 types of pump in the posture displacement only. One is the plunger type pump. The method of actuation is different. One is the plunger type pump and one is the diaphragm type pump. Generally, the plunger type pumps are a little bit cheaper and the diaphragm type pumps are a little expensive. If you see, this plunger is moving back and forth. In this, it's like a piston. So, there is a seal over here. There is a seal over here, if you can see. So, during the back and forth movement, there is a degradation in the sealing capability. So, this leads to the drift in the pump. So, it is nothing but sucking the liquid from the suction, and then during the suction stroke and during the power stroke, it is pushing it up. Okay. So now when this seal is compromised, then the rate of suction and discharge is also drifting. The same thing in the diaphragm type pump. This is nothing but SS316 material diaphragm. Over a period of operation, the elasticity and the stiffness of the SS316 material diaphragm is compromised, and that is the reason the drift happens in a diaphragm type pumps. Okay, and moreover, if there is any solid impurities or something, or just trying to build up in these valves over here, then this is not fully closing, and that will also create some undesired drifting issues. Number one, because of the mechanical thing. Number two, what happens is these chemicals are generally little bit viscous, all these chemicals. Okay, the viscosity is higher than the water. And now these chemical tanks are placed outside. In the desert, you have in the daytime almost in summers 47 degrees, 50 degrees. In the night time, you will have at least 28 degrees or 30 degrees. So you have more than 15 degrees delta. And in summer and winter, daytime and nighttime, because of the ambient temperature fluctuation, the viscosity of the chemical changes. Once the viscosity of the chemical changes, then I told you this pump will not be able to handle it. Yeah. So even that is creating a drift. Okay, viscosity and density change of the chemical drifts. That's why if you see the data sheet or the instruction manual of any pump manufacturers, the famous pump manufacturers, such type are prominent. Milton Roy, these are very reputed manufacturers. Even they say if there is any change in the viscosity or the density of the chemical, the stroke length of the pump needs to be adjusted to maintain the set flow rate. But actually people don't care, they don't know. But this is humanly not possible to every time change the stroke length. Morning one stroke length, evening one stroke length. When you have 200s of pumps, it's humanly impossible to do that, and that's why the drift happens. And yeah, you'll have different size of pumps, 1 liter per hour pump to 150 liters per hour pump, So now if you have like 500 wells of different production capacities, you should have a mix of all the sizes of the pump in your inventory. Because the one pump which is working in the field, if it fails, you need a backup. Okay, so he has to maintain the valves and other small accessories. So it's very difficult. Okay, so again I'm bringing in the IR 4.0, how to reduce inventory, how to have a uniformity, how to have a predictive maintenance, and how to have a uniform size of pumps. Okay, it will be better if we have 130 liters pump in between, covering from small size to big size. Okay, that's the point I'm trying to make over here. Okay, okay, I'll just skip this. Why I don't know. Okay. I missed some slides in between, I guess. Yeah, it's hidden. Yeah. Okay. See, now what we can do is, if we can to have a closed loop flow control, we know that we have to tune the PLC or a controller, PID tuning that needs to be done. So what we need a flow meter to measure the flow. We need a control valve. We don't call it as a control valve over here. We call it as the IRCDs. It is called the injection rate control device, because control valves are for a bigger pipes. But if you see these lines, these are all half-inch tubings. Okay, because the flow rate is very small over here. Okay, so for such a small flow rate, we use what is called as an IRCD. And for any control valve, you need an actuator. Yes, of course. So you can achieve a closed loop control action. In this case, you need not try to control the flow rate by using the pump stroke. You can put the pump stroke at 100%. That is the maximum discharge of the pump. Here we will try to control the flow rate using a flow meter, control valve, and actuator and a PLC. Okay, and same thing if you are having a multi-point injection, you'll have a Coriolis flow meter or any flow meter, but mostly we use Coriolis for this application. IRCDs for each line. Okay, I told you the challenges we have faced. See, the problem with the these small control valves is, even if you use a control valve, this is the flow equation of the control valve. Q is nothing but the volumetric flow equals to CV of the control valve times square root of differential pressure divided by specific gravity, that's nothing but the density times viscosity. See, now even the flow equation of the control valve, the specific gravity, that's nothing but the density of the chemical, and the viscosity of the chemical is involved in it. So if there is any change in the specific gravity and the viscosity of the chemical, even the performance of the control valve is being affected over here. Okay, that's what I wanted to show over here. On top of this control valve, you have the actuator sitting on top of this control valve, which actuates the opening and closing and and the orifice of, or the CV of the control valve. Okay, so that's one thing. And now I will go to the solution. One of the another, it's an IR 4.0 compliant solutions. The product is a FluidCom. That's what I told you. It's a very unique product, which we will not find in our good old instrumentation textbooks, because it's a very new technology. See, a FluidCom is a device which can replace a flow meter, IRCD, actuator, and a controller in a single device. Okay, that's all we need. Okay, so this does the function of all the components in a single device. So you just need to give a set point to the FluidCom, set point of say 2 liters per hour, and then it's going to, just a second, and then it's going to control your discharge to the 2 liters per hour. Okay, so then you have 3 FluidComs over here, and then on each line. Yeah, so it can individually control the flow rate. For example, if you need 3 liters for the 0.1, 2 liters for the 0.2, and 0.5 liters for the injection 0.3, so it can individually control the injection rates and all you need to do is have one pump. Okay, so it's a compact device, almost like little more than a feet, and 220 mm in diameter. Okay, just forget about this. So this is okay. This is how a typical chemical injection skid looks, and the entire footprint of the conventional chemical injection skid can be brought down to this size. Saving of space and weight and improved performance. Okay, you'd be interested to know how the FluidCom works. Yeah, this would be a big question. When I said it combines the functionality of a flow meter, control valve, and actuator. Okay, it's not complicated. It works on the principle of specific heat capacity of a liquid. So everybody knows what is the specific heat capacity. It's the amount of heat energy required to raise the temperature of the substance by 1 degree Celsius. Okay, so that's the formula for specific heat capacity. Heat energy in joules divided by mass of the liquid times delta T. So now we want to measure the mass flow rate. Yeah, so we just cross multiply. Yeah, this over here and this over here, and then if we know the specific heat capacity of the liquid or the chemical, if we know the delta T, and if we know the heat in joules, then we can easily measure the mass flow rate. Correct? So that's what we are doing over here. Just a second. Ma'am, would you like to have a short break or something? Because it's 2 minutes or something, or it's okay, I continue.
No problem, sir. The session is from 10 to 12. No problem. You continue, sir.
No problem? Okay.
No problem, sir. No need for break. Okay, sir.
Okay, because I thought it might be too much of information overload.
No problem, sir.
Because concentration span was 45 minutes, just last one. Anyway, I'll continue.
Okay, sir. The break will divert the concentration. So you continue, sir.
Okay.
Thank you, sir.
No problem. Okay, yeah. So if we know the specific heat capacity and the heat energy and the delta T, difference in temperature, we can calculate the mass flow rate. Okay. So now let me see whether this video plays. Doesn't play, huh? It plays. Okay, see, you can see the fluid entering, okay, over here. And then it goes like this, and like this, okay? So, sorry. Okay. You have a temperature sensor T1, okay? And you have a temperature sensor T2. And you have a heater over here, the red color thing. Okay, now let us say the ambient temperature is 20 degrees Celsius. Okay, now what happens is the T1 will measure 20 degrees Celsius over here when it comes. And then this goes through a heating stage. Okay, we know what is the power given to the heater, and there is a temperature sensor over here, PT 1000. Yeah, it measures the temperature of the heater, and then there is another temperature sensor T3 for the heater also. Okay. Okay, now it goes over here outside. Okay, now if you see this, the CV of this opening is actuated and adjusted. Hey. Yeah. So you see, when there is a heater, when it heats up, it expands. When it cools down, it contracts. So this is continuously adjustable. Okay. So we are depending upon the set point, the orifice or the opening or the CV of this valve is adjusted. Okay. So now just let me explain over here. Now let us say you have a set point of say 5 liters per hour. Okay. For 5 liters per hour set point, which the user has given, your your incoming temperature is 20 degrees Celsius. There is no change in it because it is coming from the tank. And now for 5 liters per hour, the fluid com knows that it requires say 20 watts of power to the heater. Okay, 20 watts of power to the heater. Okay, so for 20 watts of power to the heater, let us say it will generate a heat of say I don't know 40 degrees Celsius. Let's say I'm just a rough figure, 40 degrees Celsius. So now it generates at 20 watts power is given to the heater to maintain 5 liters per hour and 40 degrees Celsius. So the heater is maintaining at 40 degrees Celsius. So the T2 will be at 40 degrees Celsius. Okay. So the delta T is 20 degrees Celsius, and so we are measuring the mass flow rate. and for 40 degrees Celsius, there is a certain opening now. Now suddenly somebody increases the set point to 10 liters per hour. Okay. When they're increasing the, let us say the power in this case becomes 40 watts. And the temperature required is 50 degrees Celsius. Now what happens is it tries to open more. Now when it requires 40 watt, it drives in more, it draws more power and heats up more, and once it is heating more, it is expansion and it is opening the valve more. And suppose somebody wants to give 1 liter per hour, so it is continuously adjusting. It will see whether 10 liters per hour is achieved, and then it will try to close the or open the control valve, like a PID algorithm is there within, and it will keep the proper orifice. So like this way, it is able to measure the flow rate, and also by simultaneously controlling the orifice of the opening, it is able to control the flow rate. That's why I say it has the heater, it has the flow measurement, control valve, actuator, and the PID algorithm all in one device. So this is how this particular device tries to work. A simple thing is your pump is at 15 liters per hour, and you put 10 liters per hour set point, and this means it will allow only 10 liters to go to the process, and the remaining 5 liters will go back to the tank. Okay, so when you put a new set point, 8 liters per hour, and then this means 7 liters will go to the tank, only 8 liters will go to the process. So in this way, it is able to efficiently control and measure the flow rate all in one single device. Okay, so this is one part of it. So we are doing a smart control over here. The device itself, it's able to do the control and the flow measurement without using discrete components over here. Okay, then we will see. Okay, this I will skip it. These are all these theories. Okay. This is a live data from the Eldfisk ConocoPhillips plant. Okay, this is in the Northern Sea near Norway. Here you can see a traditional IRCD or a control valve. When we are using discrete component, how much fluctuations we had. Okay, and the same thing when we deployed the FluidCom. You see the performance was between these, between these two red lines, it was extremely smooth. Okay. One more main benefit is, suppose you have, okay, I'll just show this slide. Okay, you have 4 points over here. Then you need 4 pump heads to drive, if it is an older or the existing current implementation of a chemical injection skid. You have 4 points, and you need 4 pump heads over here. Okay, and then you need 4 pressure relief valves and 4 pressure transmitters, 4 pulsation dampeners, and 4 Coriolis flow meters. So in case you're deploying this with a FluidCom, which is IR 4.0 compliant, you just need 1 pump head. Okay, and then you need just 1 relief valve and 1 pressure transmitter and 1 pulsation dampener. And you need 4 FluidComs. So this drastically reduces the footprint and the performance of the skid. So it really doesn't matter what pump size you're using. You can use any pump size, but it has to be bigger so that it can cover the demand for these 4 points. Yeah. So yeah, here you can see a comparison of how it was before and how simplified it is now. So this is the way how it works. Okay, I'll just skip these 3 things. Generally, even this we need to take into consideration. If you're using discrete components, to your control system, you need 16 analog inputs to your controller, that is your DCS. If you're using a flow meter, control valve, and actuator, then you need power for the flow transmitter, then you need power for the actuator, and then you need 16 analog outputs to give the set point, the control values to the control valve. So you have so many signaling. But since we are in case of FluidCom, since it's only one device, then we are able to get rid of all these things, and we can daisy chain and get it to the and we can do the wireless communication as well. Okay. So, but here you need a separate logic solvers and everything in your DCS programming, function blocks, routine has to be defined, but here you need not do because everything is happening in the field. Yeah. So that's one thing. Okay, I'll skip this. Not important. Yeah, this is what is important. Okay. Now, how it is truly IR 4.0 compliant. Okay. Today, what the operators are doing is, okay, for a certain production rate of the well. Okay, let's say this is a gas well. The well capacity is like 20 million standard cubic feet per day capacity. The production is going to vary. For week 1, it will be at 10 million scarf. For the week 2, it will be 12 million scarf. For the week 3, so on. So every time the well production is changing, operator needs to intimate the chemical injection guy, and this guy needs to go from his office to the site to change the injection flow rate. Okay, so this needs to be done. It is completely a manual process, and which is IR 3.0, you can say. Now, what we are doing with the FluidCom is the well production has a Venturi-based multi-phase flow meter. Okay. Now, what we need to see is based on the water cut. What is a water cut? A well produces oil. Okay, oil. Along with the oil, it produces water and gas. Now, oil is okay. It is an organic thing, but water, it will have dissolved chlorides, sulfur and all these things. So, water is always a source of corrosion. Please remember that, because it has dissolved oxygen and many things dissolved in it. So if the water cut is more, then the rate of corrosion injection should be more. Okay, it should be proportional to the water cut, and it should also be proportional to the production rate. So we have to see 2-3 parameters and inject the chemical into this. So that's why already your well production flow meter is connected to your SCADA or DCS. So from there, what we can do is we can have a routine or AI over here, and that AI will give the set points to the FluidCom. Okay, and the FluidCom can talk wirelessly to the PLC, publishing the data from the FluidCom. That's the current injection rate values over wirelessly. And in this particular implementation, we are using ISA 100.11a wireless protocol to publish the data over here. Okay, so we have completely closed loop or cascaded or a ratio control we have done over here between the production and the chemical injection. Earlier, the chemical injection was totally independent and the well production was totally independent. Now we are tying up the corrosion and everything over here. Now what will happen is, now we have a level sensor on the tank. When the level sensor is diminishing or depleting, then automatically the purchase or the procurement will be notified that the stocks are depleting, and then they can place an order for the chemical to be replenished to the tank. So this is how we are trying to when we say digital oil field, means we are connecting all the silos, interconnecting all the silos, so the communication between different systems and different entities will happen. So they can perform in tandem and another good example I will tell you is This is an oil field example, but this is another. This also example is from oil field, but it is from the utility section. Okay, in some wells, in some oil fields, the oil rate has declined because the reservoir is already becoming empty. Okay, so or in some oils are very heavy. It is like a tar or asphalt. Okay, so it will not, the flowability of oil will not be so easy. So how do you make that oil flow from the reservoir to the surface? You have to break its viscosity. Okay, how will you break the viscosity? You cannot, of course, blow hot air inside, or you cannot pour hot water inside. So the obvious thing is you have to inject steam. Okay, this is called as the steam injection wells. This is one of the process of enhanced oil recovery. We call it as EOR. Okay, in enhanced oil recovery we inject steam. So for injecting steam, first we have to produce steam, correct? Okay, so that is why even in oil fields, some of the oil fields, for example, I can give you an example. In Kuwait, the government oil company is known as the Kuwait Oil Company, KOC, most commonly called. In KOC in South Rakta oil field, okay, in northern Kuwait, they produce heavy oil, heavy crude oil. This heavy crude oil, if you see the reference density of the crude oil, it is almost 940 kilogram per meter cube. So you can see the reference, it's very heavy. So those kind of oil, it will not flow. It will just be staying like a, like a gum, inside, like a asphalt inside. So they have to blow the steam. So now when they are blowing the steam is generated by the boiler, and we have to give the boiler feed water to the boiler. Now, when you're giving the boiler feed water to the water has to be treated, and it has to have certain pH, and it has to have certain qualities. Okay, you cannot give untreated boiler because the boiler's heating tubes will get corroded. So that's why generally we are injecting chemicals to have a certain pH of the boiler feed water. Generally, a pH of 9.5 to 10.5 is required for the boiler feed water. Okay, this has to be maintained because 9.5 to 10.5 is basic, and because they don't want even 7 or something like that, because that will be little bit acidic and it will create some corrosion. So 9.5 to 10.5 pH is desired. So they inject a chemical into the boiler feed water to maintain the pH. Now what we do is, how do we control the injection rate and boiler feed water? In the boiler feed water, we have some pH sensors over there that measures the pH of the boiler feed water, and then we inject the chemical to control the pH. So this is working on a closed loop to control effectively the pH of the boiler feed water. So that's another example of how the entire the steam quality can be met. So here I would like to show you an example. What are the process optimizations we had done? Okay. See, in boiler, we call it the Cogen 3 boiler. You can see the 5 ppm and the 20 ppm limit over here. Okay. See, when the boiler, for the boiler feed water, to control the pH, we are injecting a chemical called phosphate, sodium phosphate. Okay. The main function of the sodium phosphate is to maintain the pH at 9.5 to 10.5, which I told you all already know. But you should not inject more than a certain, concentration, because if you inject sodium phosphate more, then your sodium phosphate concentration in boiler feed water will be more than 20 ppm. It is highly not recommended, because it gives rise to a phenomena called as the phosphate hideout. Phosphate hideout, it will stick to the inner walls of the boiler tubes, and decrease the heat transfer efficiency, and your boiler will not be optimum. So that's why it is very important to keep the phosphate near to 5 ppm. This is more desired than even going to the 20 ppm. See, before using the automatic control, like what I explained in the PowerPoint slide, their pH was, their phosphate residue was jumping. It was mostly, on the higher side and erratic. But after we started using the fluid com, which we are doing the control, all the predictive thing, and then we are like, close to 5 ppm. You can see. So this means the boiler is highly efficient now, and it is going in a good direction. So these are the benefits, real-time benefits, where we can see clearly what is happening. Okay. So see this title, this is Cogen 3. Even you see this one, sodium phosphate injection rate, now the injection rate has become very stable over here. Okay. And even the pH is very stable. Now you see the same in Cogen 1, where they do not have this kind of automation, still it is erratic, very erratic. Okay, this is a pump-based control, and now it is very erratic. Okay, so these are some of the live examples. How we optimize the process, how we study the process, clients' present difficulty, and how we optimize it and give the good solution. Yeah. So this is all. This is all just where things have been installed or something. So yeah. I think so. That brings to the end of my session, and now we can have any remaining, I think so, 25 minutes or 20 minutes we can have for any question and answers or any interactions. Yeah, please feel free.
Actually, Narayanan, I want to record few things here. Would you able to get my voice?
Yes, Sharmila, I can. Yeah, I can hear you.
Okay. I'm very happy and proud to have my friend here for this session. When we had a talk after a very long years due to this FTP, we just reminded about our college times and friends. While speaking casually, we were talking about the pay, like his growth, his pay to increased tremendously. I think it's nearing 1C per annum. It shows his hard work at different stages and utilization of future technology. So I just leave to the audience to share whatever they feel to ask him.
Thank you, Narayanan.
Thank you, ma'am. It's my pleasure. So,
Hello.
Yeah, I can hear you.
Yeah, I am Kalyan Sundaram, Associate Professor from Parisvittam Institute of Technology. I'm really grateful to you. Your presentation is extremely excellent. You have exposed the entire oil and gas refineries, and especially on the chemical reactions and other things. It is extremely good. And I would like to talk to you, that whatever the instruments which you are trying to use with this chemical process, it's in hazardous locations. How
Yes,
do
sir,
you
absolutely.
protect those instruments without affecting?
Okay, so very good question. Yeah, I did not talk much about it because see, all the instruments which we use, the pressure transmit. Yeah. Yes.
Yeah. Now, what is the protection class with the quality point of view? Can say the instruments.
Okay. Yeah. So if you see Saudi Aramco, they are adopting FM or IECEX hazardous protocol. Okay, hazardous class certification.
You started
So all the
Yeah. When you started your speech, I had a lot of doubts during
all the
chemical
instruments
industrial.
like pressure
Yeah,
transmitters,
during
flow
chemical.
meters, and other things, what we are providing, it is either intrinsically safe, or explosion proof, class 1, zone 0 or zone 1, zone 2 certified.
Thank you.
So
Thank you.
any
One more
explosion that might
Thank you.
occur due
And-
to a non-expected operation or a hazardous operation, the explosion will be contained within the instrument, because it is designed to withstand certain temperature of explosion without compromising the surface temperature of the instrument during an explosion occurs.
Okay, thank you, sir. Okay, thank you. And one more question. As you rightly said, when you try to extract the oil or gas with the well head, and as you said that there is the sulfur content is there in the raw crude oil, and the sulfur content is exceeds certain limit, which will try to give rise to the acidity on the pipeline or other component where it is being exposed. How to be protect those?
Exactly.
Are you?
Yes, yeah, exactly. So during the well exploration study, the complete geology of the produced emulsion or the produced crude or the produced gas, it is known to us. Okay, what is the H2S ppm? Okay, basically H2S is the most corrosive gas, and it's a poisonous gas, and chloride contents are also present. So the samples of these things are taken to the laboratory, and it is entire study is done, a corrosion study is done, corrosion mitigation study is done, how much chemicals and what is the concentration of the chemicals that needs to be injected to inhibit these corrosion problems. Okay, so accordingly the chemical treatment and various materials which are also deployed in the downhole are designed to withstand those capabilities with a certain factor of safety.
Okay, thank you, sir. One more. So as you rightly said that this plant is getting operated through remote system, that there is a remote unmanned system. If there are gases will be exposed on the atmosphere, how to be disposed? There are some dangerous gases in the chemical plant. That particular gases, is there is any kind of an incinerator is being equipped to remove unwanted gases on the plant?
Yes, definitely.